Hi, this is Professor Stugard, and in this video we're going to go over the limit laws and also some theorems about limits. So our goals for this video are to first of all just learn the basic limit laws, and then we're going to understand how to use direct substitution to evaluate certain limits based upon those limit laws, and then lastly we're going to try to explain what the squeeze theorem is. But let's start off with our limit laws. So for all of our limit laws that we talk about in this video, we're going to suppose that c is just some constant. So it could be a 2, a -3, a 1/2, or even a pi or something like that. Again, something that's not a variable. And we need that the following limits exist. That the limit as x approaches a of f of x, and that the limit as x approaches g of x, we have to make sure that those both exist. And the key word there is they have to exist. So again, none of these limit laws work if the limits do not exist. And also remember that infinite limits technically don't exist. If we do have an infinite limit, again, we can describe what's going on using infinity. But since infinity is not a value that we could ever reach, and the whole idea behind limits is that we want to be approaching or reaching some specific value, some specific limit, well, we can't reach infinity, which means our limits don't exist. And we just put infinity to be more descriptive about what's going on. Okay, so let's jump into our first limit law. And the first one is actually one of the kind of the more important ones, or one of the ones that we're going to see most often, because we're also going to take all these limit laws that we learn and it's going to be applied later on in calculus. Our study of derivatives and our study of integrals are all going to be underpinned by this foundational concept of limits. So we're going to be using these limit laws a lot throughout the course of an entire Calculus 1 course. Now, the first one is just factoring a constant. So again, what this notation says is the limit as I am approaching a, if there's some constant I can factor out of my function, so let's say there's like a GCF of 3 and I can factor 3 out of every single term in my function, I can actually take that 3 that I factored out and I can factor it all the way outside of my limit notation too, which is really, really cool and powerful because we are going to be using that idea, well, again, like I said, a lot when we talk about derivatives and integrals as well. Just notice that, again, it has to be a constant. It cannot be part of the variable. So in this case, my variable is x. If I had a GCF of 3x, I can factor the 3. I can't factor the x, right? All the variables have to stay inside my limits. So we also have our sum and difference limit laws. So this is where we can split up limits. So pretty straightforward. If I have a function that is actually a sum, I can split it up and take the limit of each part of that sum individually, and the same with differences, right? If it's a subtraction problem, again, I can split them up, whether it's addition or subtraction, with no problem. Also, I can do the same thing with products and quotients. So again, if I have a function that is a product, I can actually factor it and take the limit of each of the parts of those products individually. And then the same thing with any sort of quotient or fraction. Again, I can take the limit of the numerator and the denominator separately. Again, we have to make sure that the denominator does not equal 0 in the case of a quotient. And of course, going back to that main idea, the limit has to exist to begin with for us to be able to do this. So if we have one of our limits that does not exist inside of a problem, well then we might not be able to apply these limit laws. Now, we can also extend this to powers and roots. So if I have a function raised to some power, like maybe a quantity x plus 1 raised to some power, I can actually take the limit of the inside part and then raise it to that power later on. This also applies to our roots and radicals because, well, don't forget that every root and radical is really just a fractional exponent. So it absolutely applies whether our exponent is a whole number or a fraction. We do need to be careful, though, that if we are dealing with a root and it is an even root, like a square root or a fourth root, we still need our radicand, or that underneath part, to be non-negative, or we would end up with imaginary numbers, and we're not dealing with that in calc. Our entire calculus sequence is going to be based solely in the real numbers. Now, we have some special limits as well. The first is the limit of a constant, and this should be fairly straightforward. If I have a constant, like let's say 2, well, then it's always 2, right? It's that horizontal line. It's always going to be 2. And so what's the limit as it approaches anything? Well, it's still 2. So the limit of a constant is always that same constant. Also, we have the limit of our identity function. So our identity function is f of x equals x, meaning I plug in x and I get x. Identity is this concept where it is a do-nothing. So the multiplicative identity is 1, because if I multiply by 1, it does nothing. The additive identity is 0, because if I add 0, it does nothing. The identity function is simply f of x equals x, because it does nothing. Whatever I plug in, I'm going to get back out. And so if I take the limit of my identity function, well, it's just going to be whatever my variable was approaching. So the limit as x approaches a of x is always going to be a, and I can just kind of plug that in. Well, then the nice part is that if I know that these two special limits, which I can prove, and I apply my other limit laws, well, that means that I also have the limit of these power and these radical functions as well. So if I have the limit as x approaches a of x to the n, well, that's just going to equal a to the n. Basically, I can just plug it in. The same thing with my roots. I can always just kind of plug it in, as long as that limit exists. And so this makes evaluating limits really nice. So this is the formal way that we think about this, and this is the reason we can do it. I wouldn't necessarily suggest you actually write it out like this, except for maybe 1 or 2 times just to make sure we understand the concept. But if I were to take the limit of this function, the limit as x approaches 2 of x squared minus 3x plus 7, well, I can use my sum and difference to, again, consider each of these terms individually, right? I have 3 individual terms inside of my limit, right? My function is a trinomial with 3 terms. So I can look at each term individually. I can look at the x squared separately, then the minus 3x separately. And don't forget that whenever we have negatives, that negative sign is attached to the coefficient in front. So it's better to think of it not as a minusing 3x, but really that is a negative 3x. The term is negative 3x. And then we have my constant term 7. Okay. Then we can go through and evaluate these term by term. So we look at that first one, the limit as x approaches 2 of x squared. Well, wait a second. We know that the power rule means I can just plug it in. So that'll be 2 squared. We know 2 squared is 4, and we're done. We can move on to the next limit. So this next limit is the limit of negative 3x. Well, that negative 3 is a constant. I can factor that constant out of my limit now. So I factor out my negative 3, and then the limit as x approaches 2 of 2. Yeah, it's just going to be 2, right? I can direct substitute. I can plug it in. So I can get negative 3 times 2, which gives me 6. And then the last one is my constant function. 7 is a constant, so it's just going to be plus 7. And so bringing that all together, the limit of my original function is just 5, which, again, we don't necessarily have to break it down every single time. Good idea to do it once or twice just to get the idea. But direct substitution makes life a lot easier. As long as our value a is in the domain of our function, then if I'm taking the limit as x approaches a of that function, I can just plug it in. I'm going to get f of a. I can plug it in and direct substitute and just evaluate. And this is going to work for every single polynomial function. This will work for every rational function on their domain. So again, that means that it's not going to work if I get a denominator of 0, but it'll work everywhere else. It's true for all my exponential functions, which are continuous everywhere, and then even the sine and cosine functions. So direct substitution is really, really nice. Just plug it in. All right. The last thing for this video is the squeeze theorem. And so the squeeze theorem, which is also sometimes called the sandwich theorem or the pinching theorem, states that if I have 3 functions where f of x is always less than or equal to g of x, and both of those are always less than or equal to some function h of x, as long as we have some neighborhood where x is near a, if that's the case, then if the limit as x approaches a of f of x, my smallest function, equals the limit as x approaches a of h of x, my biggest function, and they're both the same, well, that means my middle function must also be equal to that limit. And so, again, I think visually is the best way to try to understand this. Again, we have this set up where we have h of x is always on top, g of x is in the middle, f of x is on the bottom, and we can see that if there's a point where the top and the bottom function squeeze together or sandwich together, everything will have to approach that same limit because, well, it's just kind of trapped in the middle. And so hopefully that's not too hard to understand intuitively if we look at the graph. Okay, so that wraps it up for this video. Can you answer these questions? First of all, what are the limit laws, right? We had quite a few of them. Make sure that you know what they are. Write them down so that we can use them later. Number 2, and this is probably the most important one, but when can we use direct substitution when evaluating limits, right? When can we make our lives easier by just plugging in? And then the third one, can you explain that concept behind the squeeze theorem we just talked about? All right. Well, that wraps it up for this video. If you have any questions, please let me know. And as always, take care of yourselves.